So it's a pleasure to be here. I actually gave a talk, a Jones seminar, in February of 2010. I tried to change this talk a little bit from that. In particular, I've partly inspired, I guess, by the talk I heard a few weeks ago by Bill Davidow, which was an excellent talk, by the way. If you missed it, it's a shame. I thought I would address some of the, I call things from my dark anxiety closet, society issues that this technology that I helped bring forth has kind of caused. So I'll spend some time talking about that. And my objective here is not to give a detailed talk about image sensor technology, because I know that there's likely no image sensor technologists in the room here, but rather give you some idea about what goes on in the science and the technology of image sensors. And I don't know, I guess that is my objective. Okay, so we all like to take pictures. I'm not, it's kind of hard to pin down why we like to take pictures. I think that the main we like to share them with other people for the most part, and we like to share the experience of being there across time and space with other people through digital images. Certainly, vision is one of the key human senses. It reminds me that Bill Davidow was talking about the overconnection of the internet and how people are addicted to their smartphones, and it just keeps going and going. And he's like, wow, people just can't stop checking their mail. And I was sitting about right here, and right next to me was a student. And the entire time Bill was talking about that, he was like busy checking his mail. And he could not let go. And I don't think he even heard what Bill had to say. It was pretty funny. Anyway, we like to stay connected with other people visually, and so maybe that's one of the reasons we do it. But people have been doing this for a long time. Certainly since the 10,000 years or so ago, people were inspired to capture images and share them with other people. This tormented soul reminds me of the way I feel from time to time. So I like that. And here I'm shamelessly advertising the work of my cousin Bob Jackson, who's a painter. And then, as we all are kind of lazy, it's like a lot of work to capture an image by hand. So doing it automatically is a lot easier. And so cameras actually been around for quite a while, but one of the first, not the first, but one of the first well-known cameras is the Daguerreotype that came out in the early 1800s and lasted for quite a long time until it was pretty much replaced by the concept of using film on a spool. And that was the Kodak innovation that came in the Brownie camera in the late 1800s. Of course, SLRs like this K1000 are a big improvement over the Brownie camera, both in terms of the lens and on the way the film is handled. I had one of these cameras, that's why I chose it for picture. And then around the same time, Steve Sasson was probably the first guy to come up with a fully portable digital camera. Okay, it doesn't look so portable, but conceptually it was the first portable one. I mean, some of my friends at JPL might argue that the space program was in the first digital camera systems, but it wasn't really portable. Those were big systems. I got to meet Steve for the first time actually at the National Inventors Hall of Fame induction. He was inducted at the same time as I was, and got to chat, and my daughter, of course we're standing there with our penguin suits on and everything, and my daughter came up to me and said, "Dad, this is a perfect opportunity to take a picture of both of you together, because you don't see each other hardly at all." And I said, "Oh, that sounds great." So Steve and I stood together and sucked it in and straightened our jackets, and my daughter reached into her handbag and pulled out a disposable Kodak film camera. Steve and I were like, what? What are you doing? And that's when she snapped the picture of the two of us, which was her gag gift to me to get my picture taken on film. It was a pretty good one. Although it turns out that I think that right now, strangely, film cameras are in vogue among young people as kind of some retro way to take pictures or something. It's amazing how many will choose a film camera just for some special occasion. As many times with cameras, as Professor Harthoff mentioned at the beginning, so there's the big cameras and then the point and shoots and the web cameras. There's cameras to capture motion so that you can do animation. There's, of course, cell phone cameras are by far the largest product category of cameras. Camcorders, these are sensors that go inside your mouth for dental x-rays, so kind of an x-ray, part of an x-ray camera system. This was actually the first swallowable pill camera that we worked with a team in Israel that had the idea for this thing, but they didn't know how to fit the sensor inside, so our CMOS image sensor technology made that possible, so that was kind of fun. And then there's a backup camera from cars and security cameras, and then this is another kind of camera that's a ranging camera where you can actually measure the distance to objects. So all kinds of cameras these days. And I think everybody knows Moore's law that says that microelectronics is shrinking year by year by year, or predicted that microelectronics will be shrinking and more capable year after year. And along with that, the cameras have shrunk. This was a CCD camera around 1993, which is when the CMOS image sensor technology was invented. And you can see it was a pretty big camera system. There's the CCD, but in order to actually make that CCD work at all, you needed all this other electronics as well. And basically all that functionality now is on, for example, here's an endoscopy camera. A little less resolution perhaps, but very, very small, as you can tell. And if you are in the not so pleasant position of having one of these inserted into your body, A or B, A or B. Well, I never tried to put these inside anybody. They'd use fiber optics or something to couple inside. This is a 2-megapixel cell phone camera. Actually, this is from the second company that I was running, where we'd actually put a MEMS-based autofocus actuator inside this camera. So not only was it a 2-megapixel camera, it had complete autofocus as well. And that was 2007. Now, just 4 years later, there's a 16-megapixel cell phone camera with autofocus, and this is a centimeter scale, so it's really amazingly small. Amazing progress. But that, as I promised, brings up some society issues, and I thought I would address them first before we dive into the science and technology part. First of all, we're in an age now of very image-centric communications. I mean, cell phone cameras are really everywhere, quite ubiquitous. So whether you're on vacation or seeing your lovely wife and daughter, at Stanford, by the way, and or enjoying the winter in New Hampshire. I saved this for sharing this with my California friends. It's nice to show these pictures. Actually, this picture is not a cell phone camera. This was taken in 1999, and if there had been a Geek Award that year, I probably would have won it, because we had just come up with a very small camera, but it was still tethered to the laptop. So we had a cable that would have to run to the laptop for power. And so I went on a family vacation, and everywhere I went, I had this laptop and then this little tiny camera. And I was balancing the laptop on one knee and trying to point the camera at something I wanted to take a picture of, and hit the button and capture the picture. And I got a lot of funny looks from other people that were on vacation, but hey, it's not a bad picture for considering. But So there's these things that kind of bother me, though. I mean, I'm that I didn't really anticipate when I invented this technology. And so I'm just going to cover a couple of these. And I hope by sharing them with you, I can kind of unload myself, my concerns onto you, and maybe one of you will figure out how to address these things. But one of the ones, which again was inspired by Bill's talk, well, I mean, this was bothering me, but it inspired me to talk about it, is visual information overload. I mean, there's billions of cameras out there collecting visual information. And I don't know about the rest of you, but watching something like the Japanese tsunami, which you're practically seeing live, I just felt was very stressful. I felt like, wow, I can watch all this stuff happening, but there's not a darn thing I can really do about it. And we have this kind of godlike vision now. We can see all kinds of things, all kinds of places, and yet, we're kind of powerless to do anything about it. And then also, the kind of, let's say, the speed at which revolutions take place has also been greatly accelerated by the sharing of visual information. So it's a lot different than reading about, in a paper that such and such happened in this distant country. It's like you're right there and you're living the experience. And I think this rapid visual communications helped really accelerate the spread of, peaceful democracy revolutions for the most part, knock on wood, even last spring and summer. A second thing that bothers me is kind of a loss of privacy. When it first kind of got some publicity from this image sensor technology, I got interviewed by BBC Radio. And the interviewer asked me, are you concerned at all about the fact that we're going to have so many cameras, a big brother watching us everywhere? And at the time I said, well, not really, because there's just not enough people to watch all these cameras, so no problem at all. But what I did anticipate is the advances in software that can actually allow a computer to recognize people from facial characteristics and other things, and be able to track their movements, not only in any one camera, but from camera to camera to camera. So you can have this very automatic tracking and activity logging, which, I don't really like to feel like I'm being watched all the time and tracked. Not that I feel like I'm doing anything wrong, but somehow the fact that this is being kept on my permanent record someplace, I find upsetting. There's also loss of privacy, not just from, let's say, the good guys, but also from the bad guys. If not now, but certainly very soon, it's going to be possible to walk into a public place like a bar or a restaurant, snap a picture of the crowd, and immediately get a little pop-up display of the names of everybody that are recognized in the scene. And not only, so that's kind of cool, and go to some place, you can figure out who's there and what they're up to. But, from a bad guy point of view, figure out, oh, look, this guy's worth a lot of money, or that girl's worth a lot of money, and, we should kidnap her and hold her ransom. Or, wow, they're out of their house. We know, here's the address of where they live, hey, so-and-so's not at home. You can go to their house. And that's not like a nightmare. That's a fantasy nightmare. That's just going to happen really soon now. And then the second part is, Mad Men is Madison Avenue type things, which there was a small scene in the movie Minority Report where, if you saw this movie, he's walking through a mall, and because all the cameras in the mall can recognize who he is from biometric data, immediately flash an advertisement on the billboard that's specifically tailored to that person. And, it's bad enough to get junk mail at home or calls from telemarketers, but wow, you walk into a public place to get assaulted by all this stuff, but I don't know, it'll probably drive me insane. Anyway, it will drive me insane. I guess maybe not New Hampshire. We don't have any malls in New Hampshire. Then there's also the whole inappropriate use aspect, and I won't go into this too much because it's pretty obvious what's going on here, but it's so much of a problem they actually have to put up posters and warning people, and in Japan, in fact, it's a law that even set to silent mode, a camera has to make a loud click when you take an image, just for this purpose. And then another thing, which again is, there's kind of a good and a bad thing. It's like defense is a very important application of any technology, in particular image sensors. But we're at the age where it's going to be possible to build very, very smart weapons and very personalized weapons. I just want to say I get credit for coining this first, iBullets. Where you can, it's possible that you might fire a weapon and not really aimed at any one person in particular. That information is in the bullet, and it goes out and finds its target that way. So is that good that you don't hit the wrong person, or is it bad if you happen to be the person that the bullet is programmed to hit? I think it's awkward at best to think about. This is part of a program that's going on right now, where this looks like something out of Minority Report too, except this is also real. That it's possible to build these little creepy robots that walk around and either spy on people or actually deliver lethal things to those people that you want to deliver lethal things to. I don't know, kind of creepy. Reminds me of, I'm a big science fiction fan, as you can tell right away, but scene from the book Dune, and then the scene of the hunter-seeker assassination device that goes up and does a retinal scan. Or actually, it's trying to see if the person blinked. I forget exactly how that worked, but kind of scary. So anyway, these are kind of things that are in my dark anxiety closet, things where when we invented the technology, you don't really think about all the ways that it can be used in not such a nice way. And I think we need to kind of start to address these issues. And it's very hard when you're a technologist. You just really don't foresee all this stuff that's coming up. That's negative. And yet, I'm not sure what I could have done differently, but it's a problem nevertheless. Okay, so back to the science and technology part, which is more inside our comfort zone, perhaps. So anyway, we start with cameras, and the first thing that has to happen is light has to come in. So the light from some source, which is typically either the sun or an incandescent lamp or a fluorescent lamp, hits the scene, it's reflected off the scene and gathered by optics. And then in a conventional camera, it's focused onto an image sensor where the photons are sensed and read out. The signal is read out. And there's a lot of photons that typically come in, a lot of photons that come in. But one important part about the science is that all these sources that I mentioned, whether it's black body or some other like fluorescent excitation, the photons that come out of that don't come out of that source like water dripping out of a faucet. Drip, 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 drip. Of course, 10 to the 14th per second or something, but drip, 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 nice steady rate. They come off with at a very irregular rate, kind of like traffic on the freeway. Okay, and if you wanted to take an image, which is really measuring the photon flux rate, is what you're trying to do, is to estimate that. It's just like on a freeway. You can't just count the number of cars just for a very short period of time and expect to get a very good estimate of that. There's noise in that measurement. And in fact, the longer you make the measurement, the better and better estimate you get of the average rate of traffic flow. So we have the same thing with photons. that if we have a very short period of time, we have a lot of photon shot noise, not much we can do about it except perhaps integrate longer. It's not just in time either, by the way, it's also in space. If you have a large image sensor and you have it uniformly illuminated so that theoretically every pixel gets the same amount of light, if you go back and measure it, you'll find that actually there's quite a bit of difference. Of course, the scale is blown way up here, but there's quite a bit of difference between pixel to pixel. And you get a nice Gaussian kind of histogram in terms of the distribution of signal levels. And noise basically goes like the square root of the number of photoelectrons that are generated. And so the signal to noise ratio also goes like the square root of n. And that is not so good to have in your image. It can affect, of course, the image quality. This is a simulated effect of noise, no noise, and more of it. Not only does it affect kind of the luminance signal across here, the brightness, but it also can affect the actual color. And we'll talk about that in a little bit. Another physical thing that happens in image sensors is the diffraction limit, which another limiting factor that we can't do too much about, at least not yet. And in the diffraction limit, what that says is, hey, if I have a perfect light source, just a perfect point of light, in fact, and I go through a perfect lens, no matter how hard I try, I'm still going to get sort of a blurred output image, so-called airy pattern or the airy disk as part of the diffraction of the light. And what it says is that this diameter of the central disk, for example, is pretty well behaved with both wavelength and F number of your optics. And if you calculate that out in green light, say, at f2.8, f2.8 is about the F number that you find in camera systems on your cell phone. That means that this airy disk diameter is about 4 microns. Great. Well, the interesting thing now is that pixels in most sensors are well below 4 microns. If you take out your cell phone camera, probably the pixel pitch is more like 1.4 microns or maybe 2.2 microns, depending on when you bought your phone last year or this year. So that means that really we might have that many pixels in our camera, a lot of pixels in our camera, but the real resolution that we get out of our camera is not actually improved. So as I told you 2 years ago, this is a great example that sometimes the force of marketing is larger than the force of engineering. Okay, people buy according to the number of pixels on the box, and everybody knows that. So, hey, it may not really work that much better, but if we put more pixels on, people will buy our product instead of their product, and everybody wins, sort of. But this is a problem. I mean, there should be a slowing down of the so-called megapixel war in cameras, but it hasn't happened too much yet. So anyway, that light comes in through that camera system, and when it comes down to the sensor chip, we usually go through one more step, micro lens, which is not really a focusing, or I should say an imaging kind of lens. It's more of a funneling kind of lens. And that's because our chip usually has metal wires and other things on it which would be opaque in those regions. And what we want to do is take light rays that might have gone into the opaque region and instead diffract them to the active part of the pixel where they can be collected. So we use these micro lenses on the top to do that. You also see that there's a color filter layer here. And so if we look at it from the top view, that filter layer looks something like this, sort of green and then red and blue and green. That pattern is a so-called Thayer pattern, and it has twice as many samples in space in the green wavelength as it does in red and blue. And that's because the human eye is much more sensitive to spatial frequency in green light than it is in red and blue, so no sense treating those colors equally when we're trying to sample, and I mean this in an engineering sense, sample the image with the image sensor. And of course, the wavelengths have some overlap, but of course it means that we're kind of cheating. When we say we have a 12 megapixel sensor, it means we really have 6 megapixels, 6 green megapixels, 6 green megapixels, 6 megapixels of green. Oh, wow, I'm not doing well. And 3 of red and 3 of blue. And we have to somehow get that red, green, blue information for every pixel downstream in the signal processing part. So now I'm going to talk about for just what goes on inside a semiconductor, just for a few minutes maybe. We have to convert those photons that finally make it down into the semiconductor to electrons, and the way that works is something like this. We have silicon, which is a really remarkable material, semiconductor. It acts a lot like diamond in terms of the way it's bonded together in a crystal form. And these are very, very strong bonds, by the way. And I can put this in an electric field, and, well, nothing really happens, actually. It's just an electric field. But if I shine some light on here, so here's a photon that comes in, and it carries with it a certain amount of energy, which depends on the color of the photon. It can come in and it can actually break one of these bonds and set that electron loose to wander around the crystal. And in fact, if there's an electric field, that electron will drift in a particular direction. Not only does the electron get broken and drift away, but it also leaves behind a broken bond, we call a hole. Or it's kind of like think of it as like a bubble. And you know, if you happen to be like me and occasionally you contemplate the bubbles rising in your beer, it's very convenient to think of the bubbles moving upward in your beer. In fact, bubbles aren't anything, right? It's really the beer that's flowing the other direction. But it's a very kind of useful construct to think of the bubble as an entity that's moving against gravity. And similarly, the absence of electron we treat as a whole, and it turns out when you treat it, it's got a lot of similar properties to being an actual particle. It's positively charged and it moves in the opposite direction. So we always call this an electron-hole pair being generated by the photon. Now, as I said, each photon has a different amount of energy depending upon its color, its wavelength. And the higher the energy of the photon, the more likely it is to break a bond. So that a blue photon, which has a lot of energy, is absorbed in the silicon, maybe just 1,000 nanometers or so deep into the material, whereas other colors like green and red might penetrate much more deeply into the material before they're absorbed. So, since we hardly teach semiconductor device physics at all at this moment at Thayer, I won't spend too much time on this, but inside the semiconductor, we actually construct a device where we have an electrostatic potential well that can collect carriers, so that when a photon comes in, it breaks that electron-hole pair apart, as we talked about, and the electron will drift in this direction and the hole out this way, and we don't care about what happens to the hole. But the electron is kind of captured by this electrostatic bucket. And as each electron is generated, it accumulates in that bucket. And when we're ready for readout, all we have to do is figure out how many electrons were captured in that bucket over some period of time, and pretty much that's proportional to the light intensity. By the way, I showed the light coming in from the front here, as we talked about before with the micro lenses. But these days, and just recently, just in the last year or so, people are working on devices where the light comes in from the other side. So here's our chip, and here's all the metal wires. They're all cut in half, so you just see the cross section of the wires. and this is the silicon part. And then actually, after we get done building this part of the chip, we actually grind the backside down and make it thin and smooth. And then we put those filters on the backside and still micro lenses on the backside. So now the light comes in from the back and doesn't have to worry about threading its way between all these wires and gets absorbed. And that can improve the sensitivity of our device just a little bit, which is good because in the megapixel wars, we keep trying to make the devices smaller and smaller. It's like trying to capture rain in a smaller and smaller bucket, and pretty soon you're left with a little thimble and you can hardly catch anything at all. You want to make sure that there's nothing obstructing the raindrops from getting into the thimble. And that's what we're doing here. Except, of course, it's light. Okay, so now we talked about how the light gets in and everything, and we got the charge. It's inside that electrostatic bucket, and we have to get it out of our chip. We have to get that signal out. So one of the first ways that people thought about doing that was called a charge-coupled device. So we'll call that the first-generation image sensor, and that actually resulted in the Nobel Prize going to the inventors, Willard Boyle and George Smith. So in CCD, each one of these pixels, where the bucket is, we have to get the data out. And the way we do it, and I'm sorry, some of you heard this just a few hours ago, the graduate student part of the seminar. Imagine you've got thousands of people standing out in a football field in the rain, and they're all trying to measure what the rainfall is in that particular part of the football field. So they all stand there with their buckets and wait and wait and wait, and the bucket kind of fills up. And then at the end of the time, we decided, okay, we're done measuring or collecting. We want to get the results. Everybody, by some sort of bucket brigade mechanism, has to take their signal and pass it to the person next to them. And then they take theirs in a bucket brigade way, pass it to the person next to them. And finally, kind of in parallel, all that signal gets shifted down to the corner, to one edge of the field. And then at this edge of the field, we have a bunch of people that actually pass it only in one direction. So they all get their signal in parallel. And then very quickly, they pass it down to the corner of the field, and one person at the end has got the measuring stick that measures the water level. It's remarkable. I mean, you have to do this like millions of times if you have a megapixel CCD to get this to work. And there's kind of two things in life that I'm always amazed at. One is the fact that 747s can actually fly. And the other is that a CCD actually works. And so actually, you can actually get the signal out here with very high efficiency, even after thousands, tens of thousands of transfers. It's amazing how far that state-of-the-art was pushed in the 1980s, especially as Camcorder was being developed for mass market in Japan. They really refined the CCD device. When I went to JPL in, what year did I go to JPL? It was 1990. The chief scientist at JPL asked me to help them with a problem they had flying CCDs in space. They said, the CCD is great, but when you are doing the shifting, if there's a cosmic ray or some other kind of damage, the crystal gets damaged and it just kind of blocks the transfer of charge down this channel. So this remarkable CCD that works great stops working, and all of a sudden you get some kind of defect in it. He said, can you think about some ways to try to avoid that problem? So that's where I came up with this active pixel idea at the time, which is, and this is for the electrical engineering students in the audience here, that you create your electrons in your pixel, and then you actually inside the pixel you put the small amplifier, and that's like giving everybody in the football field their own measuring stick and a cell phone, so that they can call in the result instead of having to pass the charge along to a lot of other people. Yes, those are my 3 daughters, by the way. So Anyway, so here we have each pixel, then we have a little amplifier, and then we have the calling in is just some XY readout wires where we can select the pixels we want to read out. They go through some analog signal processing, and the nice thing about doing it this way is the recipe that we use in the semiconductor plant to make these is almost exactly the same recipe that we use for building computers or microprocessors or all kinds of other CMOS chips. So if the recipe is the same, that means that on the same chip we can easily build other circuits like timing and control logic and analog to digital converters and other kinds of signal processing to build what I termed a camera on a chip. So here's an example of one of those chips. Here's an array of pixels, and then it has some analog signal processing to do correlated double sampling, reduce the noise. AD converter, it's got a lot of digital logic on it, and a few other elements too. So basically, all I have to do is put a clock into this, and out comes digital image data. This is a cross-section by way of a modern device. That's that structure that I showed you earlier with a potential well. So if we can put all this other electronics and circuitry on it, there's all kinds of things we can do, and there's a long list of things that we need to do to build a successful camera. I won't go through all these things, except the first one, color interpolation, because I told you that we had just like 2 green pixels and a red and a blue, but we didn't have all that information at the same place. So one of the things we do in the signal processing is color interpolation, where let's say we know the exact value of this red pixel right here, but we don't know green and blue, so we just say, hey, green is probably just the average of these 4 greens, and blue is probably just the average of these neighbors, and so I interpolate to get red, green, and blue at that 1 pixel site. Sounds easy. Actually, the problem with that particular algorithm is that, hey, this it doesn't really, this uses 4 neighbors that are this distance, this uses 4 neighbors that are this distance, and then the red, which is right there, it's not really balanced if you think about all the other color processing that needs to go on. So the real color interpolation algorithms are much more sophisticated than that, but it gives you some idea about how we generate, just from having separate red, green, and blue filters to generating red, green, blue color for every single pixel. Yeah, so not to just focus on the camera capture part, but when people take a picture, they expect to see basically the same thing that they took a picture of. In fact, they expect it to look better. In fact, they even have software where you can make yourself a little thinner, perhaps by stretching or something like that, fix up your skin tone a little bit. But there's just more processing there too, because the human eye has a certain spectral response. The silicon has its spectral response, and we put color filters on top of that. And those 2 things don't necessarily balance or match each other at all. And in between there is when we have to display the device, we might be using like an LED lit LCD display, where the spectrum of the light source has its own particular characteristic. So by the time we go through all those steps, and to get this out, there's a whole lot of, let's say, light balancing and color balancing and processing that has to take place. So the state of the art is that pixel counts for consumers are in the 8 to 16 megapixel range. Go much higher for professional or aerospace applications. And I mentioned the pixel size goes from maybe 2.2 down to 1.1 these days. And there's some pretty amazing image sensors that are coming out. This is being a lot of cameras very soon. This is a 24 megapixel sensor from Sony. This UDTV sensor was something that we started working on a number of years ago because the guys at NHK, which is the national kind of television lab in Japan, they did HDTV, and it was like, well, what next do we do? So they came out with this ultra definition TV, which they have recently changed to super high vision, which, the old cameras the old TV sets used to be 640 by 480 roughly, VGA resolution, about 300 kilopixels, 0.3 megapixels. Then HDTV, which is quite common now, is about 2 megapixels, so that was a nice improvement. And UDTV is 33 megapixels. Now, if you remember at all how long it took to adopt HDTV, I mean, it was just a long time. There was all this broadcasting issues and equipment, and wow, it was really complicated. And finally, the government just said, hey, you guys got to quit horsing around. We're going to force all of you guys to go to HDTV, and they set a date, and everything had to be in HDTV by a certain date, and that actually made it all happen. Wow, now we're going to go to UDTV. Here's another case where you don't always see what's going to happen next. But in fact, I don't know about the rest of you, but I almost never get my TV programming through an antenna system. It's through cable. And the cable, it's all digital. And now they're talking about even going to just packet-based video, where it's totally flexible in terms of what the format is. So I used to think that, this is never going to get adopted in my lifetime, because look how long it took for HDTV to get adopted. But with this kind of packet broadcasting possibility, I wouldn't be surprised if you see UDTV in another 10 years or so, something like that. So it's coming. So that gets us to coming attractions. So the first coming attraction is certainly more camera phones. This is Sony's information, but here we are in 2011, and they're saying, it's about, this is in millions, so this is 1 billion camera phones, over 1 billion, and running up to 1.5 billion camera phones per year. So that's, if you think about what you have to do to make 1 billion per year, I mean, it's a lot. It's like, it's practically audio frequency at which camera phones are coming out of the factory. Okay? It's really amazing. And, think green, that means there's like 1 billion plus camera phones going into landfill every year as well. Because how long does your phone last? 2 years, something like that? So they all have to go somewhere. It's pretty remarkable how quickly that is piling up as well. And then according to Sony, and everybody has their own forecast, by the way, but according to Sony, that just in a couple of years now, maybe 20% or so of the camera phones will all be at 12 megapixels or higher resolution. This is a trend chart. This is, we talked about the light coming in from the front or from the back. This is just a chart that shows pixel size. Here it is out at 4 microns, 2 microns, 1 micron, and kind of the switch over in technology from front side to back side. And this has just happened in the last year or two. So most of the newer cameras that you'll buy, especially if they're very small pixels, will be backside illumination. Another coming attraction will be, here's no surprise, smaller pixels and more pixels. And we talked about this a little bit before, but smaller pixels allow smaller chips. So if you make them smaller and you want to make a 10 megapixel chip, the chip is smaller. And that means that you get more chips on a wafer. That means that they can be cheaper. And that means you can make more money. It reduces the optic size and cost as well. And also people really want small camera modules because it's a lot easier to integrate them into consumer products. Certainly cell phones were one example of that. But now, it's hard to buy a display practically that doesn't have a little camera embedded in the display. You see them in the bezel of your iPad perhaps, or all kinds of places. So it's exactly like what we were talking about before, about the ubiquitous nature of cameras. They're just getting so cheap and so small that they're just going everywhere. People are going wild. Of course, the downside is that the non-recurring engineering costs for the chips are higher, and their performance is usually degraded. So that's too bad, but the number on the box still is important. So smaller pixels also means that for the same chip size, you can make more megapixels on that chip. So for the same optical format, you can put a bigger number on the box. But also, more megapixels sells more cellular cellular service traffic, bigger computers, more sophisticated software, mass storage devices. So there's a whole ecosystem, that business ecosystem, that's enhanced by selling more megapixels to consumers. Yeah, there's some negative things with it, which I'm sure you've read by now. So getting back to that subdiffraction issue, here's an example of a 0.9 micron pixel pitch. And there's the airy disk diameter. And basically, this is all fuzzed together, all blurred together. So, there should be some limit, right? I mean, at some point, people are going to wake up and realize that they're not getting that much more resolution out of their camera, because it's just fundamental. So a couple of years ago, a friend of mine asked me to write a chapter of a book about the future of digital imaging. And so I sat and thought about it, and having a very strong physics background, I thought, well, what do we always do? We just always take the limit, right, where things are going to. And the best we could do is count individual photon events on the plane and go to really small pixels. I said, okay, let's explore that. And yeah, I'm going to skip the slide. So I started thinking about that and came up with this idea, which is actually a large part of the reason why I'm at Dartmouth, because I want to explore this idea farther, this quanta image sensor. There are other ideas, too, that may change the paradigm. I'm going to come back to the quanta image sensor in a moment. There's also 3D ranging, as I talked about at the beginning, and certainly I won't talk about this in detail, but there's a whole field of computational imaging that is kind of coming along, that where you maybe you collect the information on the, I won't call it the image plane, but on the sensor anyway, that may have been adjusted by the optics, and then you use mathematics or computing to create the image from that. But if you collect the data in the right way, for example, maybe mathematically you could change where the image is focused. So there's a company that's trying to launch cameras in that area where, wow, you take a picture, but you can adjust the focus later to any point you want to. I don't actually think that's going to go anywhere, but we'll see. As part of a planoptic sensor, we have multiple lenses in small arrays, so it's kind of like a fly's eye kind of thing, where you combine all these little small images using computing to create one nice, beautiful, big image. So also possible. So let's just talk about two of these things, my favorite one here and my other favorite one there. So talk about, well, let's make really, really small pixels. In fact, it's so small, we're going to make them so sensitive to a single photoelectron, and we're going to make them so small that it's just going to be binary output, a 0 or a 1. And then it's not really part of the picture entirely, so I said, okay, it needs a new name. So I called it a jot, which comes from the Greek iota. It's kind of the smallest possible thing. And the only thing a jot does is change from a 0 to 1 when a photoelectron is present. So, and then we're going to put billions onto a single chip. They're going to be very, very small, maybe 100 times smaller in area than pixels today. In fact, it's so small that you could have a billion of them on a very, very tiny sensor, just 4.2 millimeters by 2.4 millimeters. So it really changed the paradigm of image collection, because the way image sensors work now, that bucket that's out on the football field collects all the raindrops, or photoelectrons in our case, and at the end you measure how much is in the bucket, and you decide what the light intensity must have been on average over this square to the pixel, and in this case I made it gray. I said, okay, that many photoelectrons corresponds to this intensity of gray. But in the quanta image sensor, we want to count photoelectrons. And so we're going to make really, really tiny jots, and a lot of them. And when they hit, they're just going to create basically when they hit, they'll flip the jot from 0 to 1. So it's a kind of a bit plane, binary bit plane. It's just ones and zeros. And then quick before any of these get hit more than one time, generally speaking, we'll take another image and another image and another image. And so basically, both in space and in time, we've counted up all the photoelectrons that have hit this particular sensor. But here's the difference. In this case, the pixel is a physical boundary from pixel to pixel. In this case, where is the pixel that we want to create to add up all these things? Well, it could just be this whole thing in X, Y, and Z, and we just count the number of hits in there and say, okay, that's our pixel value. But we could also be a little different about it. We could take, let's say, a weighting or Gaussian kind of convolution over this in time and space, so that we're actually counting something from the adjacent pixels as well, and something in time, forward and aft here, and create our pixel that way. In fact, we don't even have to decide when we're taking the picture how big the pixel is going to be. It can be later that we can decide what our time resolution is and what our spatial resolution is. So we have a lot of flexibility. Yeah. Not only that, I show these bit planes stacked up nicely and lined up with each other. But really, if there's motion in the image, then from bit plane to bit plane, there's some change in the center of the object or something. So instead of adding them up in an aligned way, we could actually shift them relative to one another. So we're kind of tracking the motion, and then when we do the addition or summation across all the planes, we take out the image blur. And we don't even have to decide that in advance either. We can take the data and then do some sort of gestalt processing on the image to figure out what the motion flow is in the image, and then go back and take out the blur, because we have all the original data. So a lot of interesting things we can do with this paradigm shift. This just shows a topology of how we might do this. This is like maybe 0.1 to 10 gigajots in the array. We need some sort of column sense amplifiers to detect whether it's a 0 or a 1. And then we have maybe some processing, and then we have some image formation processor. And somewhere between here and here, here's a challenge. Not only do we have billions of bits or jot data, we're going to have 1 to 10 terabits per second of data that's coming off this chip. So my graduate students, who I think are still here unless they bolted after hearing this, have to solve the problem of how we're going to build something that's 100 times smaller than things are built right now, and how we're going to put billions of them on the image plane, and how we're going to read this data off at terabits. So this is, that's like a big number, okay? That's trillions of bits per second. And then how do we create an image back out of all this data? So this is pretty much the challenge ahead. I'll just mention one other thing quickly that also I mentioned ranging sensors, and here's an example of how that works. We send out pulses of light. We measure the time it takes for those pulses to come back, and from that we can determine the distance to the object. So there's a number of companies that are working on this in the future. For the future, this is one that my group at Samsung has been working on. And in this image, you can see the range. It's all color-coded according to range, so hands are closer and the face is farther back. And you see that you can see each finger distinctly, and this is because this type of sensor will be used for gesture control, whereby how you move your fingers might control some device or instrument or TV or game or something like that. So it's very important that we can see fingers, which we can. This is the distance versus the actual distance, and in fact the error is well below 1%, by the way, in that ranging process. That's my device right there. And then we want to combine this with normal images. These are very recent results, not even published yet. And the vision here is that we take a picture with a cell phone that does both range and XY color. And, well, heck, I worked for Samsung part of the time, and they want to sell 3D TV sets. And you can already go out and buy a 3D TV set. How many of you bought a 3D TV? Well, I know why. Because there's nothing to watch on it, right? So what we need to do is to enable the generation of that media, okay? Whether it's from cell phone cameras or camcorders or even broadcast studios. And one way to do that is to incorporate this ranging so we can generate the 3D data for a 3D display. And in this case, we've actually embedded in a RGB sensor pixel that's sensitive to the time of flight, as I talked about briefly. And here's this is another color-coded range image taken in the lab from this sensor. So it's not color from the color pixels. This is just according to distance from the object. And you can tell pretty much what's going on in the scene here, but we're looking at the actual distance, not the object itself. So, hey, my conclusions are, well, okay, I listened to rock and roll too, but so life's been good to me so far. Knock on wood. Image sensors have come a long way since the first generation device at CCD. The second generation device, which is my device, is going strong, billions and billions served. I think there's a lot of interesting work ahead as we move the digital divide as close as possible to the digital nature of photons, so we'll see how that goes. It may be too hard of a problem, but I think it's pretty interesting. And again, inspired by Bill Davidow's talk, which, by the way, it's got to be the best talk I've seen in the last 10 years. And he did it without a single PowerPoint slide, by the way, standing right here. But anyway, this overconnection of billions of massive information gathering engines, that's what a camera is, leads to all kinds of interesting society issues and questions. So thank you for your attention.
Sensors similar to the size of the 35mm camera, for example?
Well, the sensors are getting quite large, so they're pretty much, there are some that are just about the same size as 35mm film. So yes, and bigger, actually.
Sure. And you mentioned the panoptic camera concept, and yesterday in the New York Times, I think it was yesterday, they had a story that you can start buying it now. Deliberately change.
Litro, yes.
Litro, yeah. So, which of the technologies did they use, that particular company?
Yeah, I think, so they are using, to the best of my knowledge, which isn't very deep, but it's a pretty good guess, they're using a commercial 12 megapixel sensor, and they're producing, because they have lots of different, it's a planoptic kind of camera system, so they say, oh, we capture 11 million rays, light rays, instead of 12 million pixels. And then they have to do a lot of processing to do that. And in the process of doing that, they give up spatial resolution. So the output image is maybe at best kind of HGTV resolution. And this is one of the problems with that approach, is if you try to approach the right spatial resolution, you need a really big chip. So it's kind of good for me. I mean, if I'm trying to sell gigapixel kind of devices, you know, if they're successful, that's kind of good. It helps drive this new technology. On the other hand, I think that it's a novelty, but all you can really do is just change the focus. And I don't know. I usually don't change the focus after I take a picture. Maybe sometimes it might be nice to tweak it, but so I don't know. I don't know where to go. Renning, I wish him luck. He tried very hard to commercialize that technology for a long time by licensing it and got no takers. And I think he just finally decided, heck, if no one else is going to do it, I'm going to try it. And
can I ask another question? Sure. So I know that there's a lot more interest in high dynamic range photography, which is, as far as I know, being done basically in software. Is there a way to build sensors that sort of have higher dynamic range?
Absolutely. It's sensors with high dynamic range the technology has been around for quite a while. So it's just been a technology insertion thing. It's just been really hard.
Make it into devices.
Yeah, nobody really wants there's some trade-off that you have to go through. It's not a big trade-off, but it hasn't been enough to warrant the use of these devices that do exist. So it's kind of like a solved problem, but anyway, I don't know what to say.
I have a quick one. To the societal issue, are there jamming devices out there? Are people working on ways to counteract the images that are being collected?
I've heard of movie theaters trying to install some sort of near-infrared system that jams people that are trying to illegally record movies as they come out. I don't think it's worked very well. For general surveillance, besides some magic cloak kind of technology, which maybe not be so magic, but it's kind of hard because it's visible light spectrum. So you could blind the sensor, maybe. You could try to blend in, but it's just hard to escape.
I will cut this short now and invite you to speak with Professor Fossum if you have further questions. Thank you very much.